Greetings, fellow adventurers, and welcome back to my channel. It's a pleasure to have you join us as we uncover the secrets of Littlewood subordination theorem. In mathematics, the Littlewood subordination theorem, proved by J. East Littlewood in 1925, is a theorem in operator theory and complex analysis. It states that any holomorphic univalent self-mapping of the unit disk in the complex numbers that fixes 0 induces a contractive composition operator on various function spaces of holomorphic functions on the disk. These spaces include the Hardy spaces, the Bergman spaces, and Dirichlet space. As we transition, let's shed light on subordination theorem and its relevance to our ongoing exploration. Let H be a holomorphic univalent mapping of the unit disk D into itself such that equals 0. Then the composition operator CH defined on holomorphic functions f on D by CFH defines a linear operator with operator norm less than 1 on the Hardy spaces, the Bergman spaces, 1p and the Dirichlet space. The norms on these spaces are defined by f sub I over a pinta pi a 3 theta d f app equal I over p int d f t f mathcalled equal I over a p int d f primes c I over a p int d partial x plus partial y c. Let's now turn our gaze towards Littlewood's inequalities and explore the fascinating connections it has to offer. Let f be a holomorphic function on the unit disk D and let H be a holomorphic univalent mapping of D into itself with equals 0. Then if 0 are 1 and 1p. This inequality also holds for 0p1, although in this case there is no operator interpretation. As we transition, let's shed light on case p2 and its relevance to our ongoing exploration. To prove the result for it suffices to show that for f a polynomial, c f, let u be the unilateral shift defined by f. This has our joint u given by us over z. Since f equal this gives f as oof, and hence c third hoof. Thus, c hath hoof a c hoof. Since oof has degree less than f, it follows by induction that c hoof uf uffa, and hence c fuff. The same method of proof works for our and. As we venture forward, let's take a closer look at general Hardy spaces and its impact on our understanding. If f is in Hardy space, then it has a factorization. For f is false, with fi an inner function and fo an outer function. Then f. In the upcoming section, we'll be shining a light on inequalities. Taking 0 R1, Littlewood's inequalities followed by applying the Hardy space inequalities to the function f was furs. The inequalities can also be deduced following using subharmonic functions. The inequalities in turn immediately imply the subordination theorem for general Bergman spaces. If you found this video helpful, give it a like and share it with someone who might benefit from it.